I would like to warmly welcome all of you for this first webinar organized in the frame of the KNOWSKITE-X project. Of course, I would like to thank Francesca, Claudio, and Laura, who are the organizers. And for today's, the topic is on modeling, multi-scale modeling, and we will discuss some mostly fundamental aspects with our two senior professors. Firstly, Jean-François Paul from the University of Lille, and he will give a presentation on atomic level modeling using DFT methods. And right after Jean-François's lecture, we will have another course by Paolo Canu. He's a full professor at University of Padova, and he will give a presentation of in the frame of middle scale modeling and kinetic modeling. But I'm sure that you will have much more details listening at those two presentations. And after those two pedagogical lectures, we will share some discussion time and a kind of round table around what could be made, what could be done or improved, and how can we use modeling at best for designing new materials. So I'm giving the floor to Jean-François.
Thank you. I will try to share the presentation if I can. Okay, so when you want to model something, the first thing that you have to do is to think about the time and space scale of your system, because depending on the type of these scales, the type of modeling and the type of tools that you will use will completely change. So today I will try to uh, yes, it would be better. Today I will discuss about the lower scale, so I will briefly present some example of atomic simulation, which correspond to nanometers and nanoseconds. And after that, I will go back to quantum mechanics and to the classical DFT calculation, which correspond to what we are supposed to do in the project. So the idea is to give you some idea of what can be done and what cannot be done, and what you have to look at if you want to be sure that that the models that you try to apply or want to apply will give you some reliable results. So I will start with some small outline, but it's not, and I will start with the atomic simulation. So atomic simulation is a relatively simple modeling. The idea is just to solve the Newton equation of motion, so it's easy. From a calculator point of view, it's very, very fast. And the idea is to follow the trajectory of the system for a relatively long time, nanoseconds or microseconds. To be able to do that, you need to have a very fast way to evaluate the forces between the atoms. And the classical way to do that is just to use a potential that will depend on the distance, the angle, this type of things, and also of the charge of the system. This type of calculation are fast, no problem at all, but the quality of the results will strongly depend on the parameter. And you see that even for a very simple system, you have a lot of parameters. Typically, for example, you also, if you put ion on your system, you will also have to adjust the value of the charges. Otherwise, the interaction will be too strong compared to the other one, and nothing will work. Uh, some other limitation to this type of calculation, they are not well adapted to metals, because on metals the number of bond is changing a lot. For example, on complexes, or the number of bond is quite large on solids, so it's always a problem. And another point is that it's very difficult, I would say, to create or to delete bond during the simulation, which means that it will be difficult to really study reactions with this type of system. So it's very good if you want to see what is happening in liquids, if you want to see what is happening in gases, this type of things on how it evolved during time. But if you really want to see how things are reacting, this type of molecular modeling are not so well done, or will not give you some so interesting results. Some improvement may be done using artificial intelligence for the designing of this type of potential. Uh, they are built quite rapidly. The problems is that you don't have the exact meaning all the parameters that are included in the calculation, and so using you will have to build another force field if you switch from one model to another one. It may be discussed, but in general, it's what is supposed. So in very simple case, it's still possible to study reaction. And I will show you an example for a system which is an ionic system. And in ionic system, if I go back, the most important parameter will be this one, and the forces between the atom can be included in the electrostatic potential. It means that you can have a relatively good description of the system without uh, deciding at the beginning which type of bond are created or so if you want to consider a reaction, you have to go from one state phase to another phase and to go over the barrier. To be able to define the reaction, you need to define the reaction coordinate, which is not always easy. And another point which is very important is that when you use molecular dynamics, you need to use enhanced sampling techniques if you really want to go from one minimum to another one. Otherwise, you will stay there if the energy of the barrier is over kT. So one way to go from one minimum to another one is to use what is called metadynamics. It's one of the examples that of the system that can, or the tricks that can be used to go from one place to another one. And the idea is just to add from time to time energy on the potential energy surface. And you can see here, for example, that the molecule or the point start here in this minimum, and we add energy to the potential energy surface. And so at the end, it's allow the point to move from one coordinate to another one. If you consider the normal dynamics, you will see that here it stay where it was placed at the beginning. And so it was not able to see and to elucidate what's how or how the reaction occur. So it's very important to know that classical dynamics, if you just let it run for a long time, nothing will happen if the barriers are relatively large or if they are above, I would say 10 or 5 or 10 KT, the system will stay on its first minima and will not explore the potential energy surface. To show you the difference, we have done some calculation on alumina, which is an ionic solid. And we started from the same point here. This is the classical dynamics, and we start from a liquid, and at the end, nothing seems to happen. The system stay in the same state. And on the second place, we add we have done metadynamic simulation, and you can see that starting from one minimum, we were able to arrive to another one, which seems to be more crystallized. So normally it should be more stable than the starting point. So this is almost all that I want to show you about uh, classical simulation, because what we are interested in this project is mostly reactions, and so we will switch to quantum simulation. The idea here is to do some ab initio calculation, and as you all know, we have to solve the Schrödinger equation. H is the Hamiltonian, C is the wave function, and E is the energy of the system. As you also know, we don't have any way to solve it analytically, and so we have to do some quite a lot of approximation to be able to get the energy of the system at the end of the calculation. So the first one is to use the Born-Oppenheimer approximation, which means that uh, we will consider that the atoms are fixed. And in opposite to what have been done for the classical mechanics, now if the atoms are fixed, it means that we don't include any temperature in the calculation. We don't put any uh, kinetic energy in the system. So the nucleus are, the atom are fixed, and we will try to solve the electronic part of the Hamiltonian. If we look at it, you have here the, the kinetic energy, you have the potential created by on your system, and this only depend on one electron, so it's easy to solve this type of part. And you have the electron-electron interaction. And due to this part, we cannot solve anything even except for H. So we will do some further approximation. On the two classical one are the Hartree-Fock and post-Hartree-Fock method. I will present you quite rapidly. And after that, I will show you that why people now prefer to do some DFT calculation in order to get some hint on some on the reaction path and to have some idea of the activation energy and things like that. So the idea of the Hartree-Fock method, which is used for molecule, for example, is just that you just have to reduce the energy to minimize the energy of your system, depending on the parameter of your wave function, and it gives you a way to define some orbitals and the energy of the orbitals. And that's what we want to compute and calculate. But to do that, we have to compute the electrostatic interaction, and the interstatic interaction uh, can be divided in two parts. The first one, which is a classical Coulomb repulsion between the electrons, and another part, which is called the exchange and correspond to something which is fully quantic, and you don't have any equivalent on this type of interaction if you just try to perform classical calculation. That's also why it's important to use quantum mechanics if we want to describe what is happening at the electron level, because we really this part is very important in the calculation. The Hartree-Fock method works well. It can take time to do calculation, especially if you have quite a lot of atom on your system, but it has always a problem. And this problem is that the energy that you can uh, get with the Hartree-Fock equation, Hartree-Fock method is always higher than the energy of the system. And the difference between these two one is called the correlation. And this part can be quite important depending on the system you are interested in. And the reason why it occur is that the Hartree-Fock method is a mean field approximation. So it means that if you consider two electrons on a system, so this one is a simple one, is H2, and you have two electrons. Formally, the interaction, the probability to find the second electron depend on the position of the first one, and they try to avoid to be on the same plane, same place, because the electrostatic repulsion will be too large. As it is a mean field approximation, it means that the electrostatic potential that the first electron sends is average over all the possible position of the second electron, and so it's completely flat. And so the position of the first electron does not depend on the position of the second one, which means that in most of the time they are too close from each other, and so the total energy that you get is higher than the normal energy of the system. And this effect will be very important when you have lot of electron in a small volume. And lot of electron in a small volume is typically what you have when you consider transition metal, because you have all the electrons that are located in the d orbital, and the size of d orbital are quite small. Some method have been developed to go further and to try to compute this uh, correlation energy, but so quite a lot of them exist. But the problem is that they all these methods take a lot of times, and the calculation time increase really a lot when you go from classical artifact to post-artifact method. And most of them are very difficult to implement on periodic system. And so it means that most of them are limited to molecular calculation. That was for the first way to do the calculation. And now we'll skip to the classical DFT calculation, which is the way to do calculations that is used now because it's faster than the previous one. So what it is that all this theory is based on some theorem at the beginning. And the first one just tell you that the only thing that you need to define to get all the property of a system is the electronic density of your system. Means that if you can compute the electronic, or if you have one electronic density of your system, you can determine the number of electrons that you have on your system, which is just the integral of this electronic density, and the external potential generated by the nucleus. So it means that you will have something which depend just on this parameter. So instead of having to compute all the orbital for all your atom or all the electron, you just have to compute the electronic density. Once you have it, everything is done in theory. The second important thing is that it's possible to compute the energy from this electronic density. You have the effect of the external potential, and you have what is called the exchange and correlation energy. So the exchange and correlation energy are the same as the exchange and correlation energy that was introduced for the Hartree-Fock method. So you start from this density, and at the end, you get the energy of your system, which is what you want. The third theorem, which is important, just give you a way to define this density. And it's similar to what have been done for the Hartree-Fock calculation. You just have to minimize the energy of your system depending on all the parameters that you introduce to compute the density. So you minimize the energy, you will get a density. Once you have the density, you can compute all the property of your system, which means that you can compute the forces and perform some optimization. You can compute the second derivative and get the spectra, all this type of thing. Everything is included in the calculation. So the problem is that we don't know the exact form of this exchange and correlation part energy. And so one first generation of density functional theory have been developed, the local density approximation, and it means that this energy exchange and correlation will just depend on the density of the system. This the expression of the exchange and correlation energy have been computed exactly for homogeneous gas, electron gas, and the same formula are applied in molecule. So we just consider that you compute it point by point, and you consider and you just get the value of the density at the point. This give you relatively good results, but some systematic deviation have been observed. And for example, all the distances that you can compute between the atom are too small. So it means that this first approximation was not enough. So a second generation have been created. And instead of using only the density at a point, you also consider the gradient of the density at the same point, which means that you will introduce somehow the fact that the density is not homogeneous and that you have some variation of the density. When you are far from the atom, this gradient is almost zero, and so you get the classical system. When you are not so far, or when you are between two atoms, the gradient is more important. And in this case, in this case, you can take into account the evolution. So these functional are still local because you just compute it depending on the value of one position, but it take into account the evolution of the system. Some other generation have been proposed later. Instead of just taking the gradient, you introduce also the Laplacian, the second derivative of the density, to introduce and to get more flexibility in your calculation. Some parameter and some constraint are known to this function, and so people have tried to develop some way to compute the energy or the exchange and correlation energy using the density. And the classical one, for example, are PW91, PB86, and quite a lot of them. Uh, this way to compute the density give relatively good results. And the most important thing is that you can apply them for almost all type of systems. The problem is that you will never get an exact solution, and you may think that choosing another type of functional, you may improve your property, but just for one simple system. So it's always a problem how to define the good functional to do the calculation, and the good functional will depend on the type of properties you want to compute. So it may be quite tricky from time to time to know exactly how to do the calculation. But in any case, uh, this DFT is a cheap way to introduce a correlation, and so it's a cheap way to do calculation with metals. And that's why now most of the calculation are done at the DFT level. Uh, I may say that uh, so you have the molecular mechanics. So this is an idea of the size of the system that you can use. For molecular mechanics, you can have tens of millions of atoms. It's easy. For at calculation, you can go up to 1000 atoms or 300 atoms. It's almost the same for DFT. And another thing is that if you consider the Hartree-Fock method, in the Hartree-Fock method, the exchange is computed exactly, but you don't have any correlation. In the DFT, you have an estimation of the exchange and you have an estimation of the correlation. So people have tried to mix both of them, and so they take, so it's what is called the hybrid method. The classical one is BSWLIP, for example, and you try to get the best of all of them. So you use the Hartree-Fock to compute the exchange, and you use the DFT to compute the correlation. And it's quite fast. The calculation are as fast as the classical DFT calculation, and you can go up to 300 atoms quite easily. If you want to go to higher level, so real post-Hartree-Fock calculation, the number of atoms will be reduced quite rapidly. So all these type of things can be used in molecular calculation. And one of the great advantages of DFT is that it's quite easy also to implement all the calculation in periodic system. And in periodic system, it's really easy to do calculation up to 1000 atoms, and it takes a few hours. So it's not so long. And that's why people are now using DFT to do the calculation. Uh, some idea of the accuracy of DFT. Everything will depend on the parameters that you put on your calculation at the beginning, because you in DFT you have still some parameters. And one of the most important one is the basis set that you use to do the calculation. So it's the basis set on which you will develop your density, and you'll need a relatively large basis set to be able to get good results. If the basis set is not large enough, you don't have enough flexibility, and so the densities that you will create will be quite far from the exact one, and so the energy and all the properties will be also quite far from all from the exact one. Uh, if you consider the distance, this is an idea of the accuracy. It's 0.03 on 3 for distance, and it's around 1 degree for the angle. Well, well, not a lot, not much better than 1 degree. For some heavy element, you will have also to introduce some other parameter. Uh, you will have to take into account some relativistic effect, and it means that to avoid to do relativistic calculation, all the effect of the core electron will be introduced in a pseudo-potential or in a potential. It means that you will not compute explicitly what is happening to the core electron, and you will only do the calculation on the valence one. And for transition metal, for example, you will have also to introduce some kind of spin-orbit interaction, just to be able to describe correctly the magnetism of the transition metal atoms. And to do that, you need some semi-empirical parameter, and the accuracy of your calculation will also depend on the choose that you have done for this type of parameters. So it's maybe a problem. Some of the things that can be computed using DFT that are relevant for the project. It's quite easy to compute the frequency, the vibrational frequency, and once you have the frequency, you can compute the ER spectra. It's quite fast, and the agreement between the calculated properties and the exact property is good. And the intensity also can be computed relatively easily. You can compute Raman spectra, but the intensity are less accurate than what you get for the ER calculation, infrared calculation. And if we consider other type of spectroscopy, we can also consider some XPS properties, but it's quite difficult to compute the absolute XPS energy, so the absolute system, but it's possible to compute relative energy. So it means that if you have different type of atom, different type of position on environment for the same element, you will be able to compute the difference in the binding energy for all these type of atom. And for example, you can compute quite easily the difference between the binding energy in the bulk and the binding energy at the surface. And this type of information may be interesting and can be also obtained experimentally if you have a synchrotron that you can change the energy of your X-ray electron at the beginning, X-ray photon at the beginning. So you can be more sensitive to the surface than on classical XPS setup. So now that we know what we have to do the calculation, we can go to the model, and everything will also depend on the models that you use to do the calculation. So how to build a model to be able to get the properties? Uh, If we consider the classical catalyst, which are equivalent to the electrodes, you have two possible way to do things. You can use a cluster. So you will define a catalytic site, and you will consider the interaction of one molecule on this site, or which means that you have just one molecule on, so the coverage may be quite low, or you can go to periodic system. In this case, you define a supercell, and it's just the opposite because you will have large coverage on the surface because you will have an atom in one molecule in each of the cell. So some example of calculation on cluster for just how to model silica. Uh, this is relatively the smallest models that you can use for the absorption of a metallic complex on silica. It's the properties that you can get using something so small are not so good. The classical one, which have been used for a long time to mimic the properties of silica surfaces, it's not so bad. Even if the number of atoms is quite small, it's just because the system is quite constrained, and so you don't have a lot of degree of freedom around the atom on top of the system. Some higher system have been, or larger system have been proposed, such as this one, which introduce some flexibility. But the problem is that you will have to cut part of the silica, and so you will have to deal with the bonding bond. It means that you will have to cut here between silicium and oxygen, and to get something which is quite neutral and easy to compute, you will have to add some hydrogen on top of it. Another way, if you want to do some molecular calculation, it's just to mix between DFT and classical mechanics. So the one place of the system is computed at the DFT level, and it's the place where you will consider the reactivity of your system. Here it's the absorption of one molybdenum atom. And in order to introduce the constraint of the bulk on all the electrostatic field, you just put a classical atom around, and you compute the effect of this second layer on the energy of the first one. But the problem is that the result will also depend on the way you cut your model. So you have some the advantage is it's quite easy. You know where is your active site. The problem is that it's not easy to define something large enough. It's just the opposite for periodic calculation. So you consider that you have a crystal, and so you can use all the trick of uh, calculation for solid in this type of system. And you can compute almost everything in a periodic way. So you can put one small molecule in a large cell, and it will be alone, so it will be a gas phase. You can consider a solid and create some defect, and you will have a repetition of the defect, but if the cell is large enough, you will not have any interaction between the defect, and so you can consider defect. And it's the same for surfaces. You can create surfaces. You just need to add a vacuum here to be sure that you can avoid any interaction between the upper layer and the lower layer. And it works well. So clusters, that was what I was saying. It's simple. In general, the calculations are quite fast. You have a lot of tools to analyze your results, and it's a classical chemical intuition. The problem is that it's low coverage, and it's always difficult to know where to stop. It's just the opposite for the periodic. Already, it's quite fast. Uh, you have a relatively good coverage. You can compute reaction rate and things like that. We'll see that. The problem is that you don't have so many tools to analyze the results. And generally, you have to deal with the density of state and the energy, and that almost and the charge of the atom, and that's almost all that you can get. And it's not always easy to build the surface, to have something which is reasonable. And another problem is that you are supposed to do calculation on neutral system. You can do some calculation, introduce some charges, but in general, the results are not so good. I will give you some example of what can be done. It's calculations that we have done in the lab some times ago. This is an example. It's an absorption of molecule on a catalyst, and the catalyst for the hydrodesulfurization is molybdenum disulfide. And the interest is that it's easy to absorb CO and to get the spectra of CO on this type of system, and to try to use the CO as a probe molecule to define what are the active sites of this catalyst. So if we want to do calculation, we need to build a model. And if you start from a crystallographic database, you can get an idea of the molybdenum disulfide structure, and you can define plane on which you will consider the reaction. Uh, This calculation have been done using VASP, a classical program to do periodic DFT calculation. And here you have some of the parameters that can help you to know if the calculations are done correctly or not. So you have to know which type of DFT has been used. So it's a classical one, PBE one. And you have also the size of the basis set, and for periodic calculation, the size of the basis set is defined by the cutoff energy, and here it's 300 dV. For calculation with VASP, now you will see that people are using 500 EV most of the time, and it will give you something which is normally correct. The second problem is to build the cell, and I can cut it. Here we have an example of a 4x4 cell, 4x4 system to define the periodic cell. It means that we have four molybdenum atoms. It's a way to reduce the interaction between the CO because the cell is quite large. And the other system is that we have four layers of the system, four layers of MOS2. And it means that we can consider that the two first, the first one and part of the second one will define the surface, and the other one will define what is supposed to be the bulk. And so the two surfaces are far enough from each other to have something which should be a bulk between them. If we had cut it there, for example, in the middle, all the atom will be on the surface, and so we will not have any bulk inside. Also, it means that we will get results, but there will not be relevant to the models that we want to the experimental data on which we want to compare them. So it's important to be sure that the size of your system is correct depending on the type of property you want to consider. So here you have the result for the adsorption of CO. One part is for the adsorption of CO on the alumina on the OH group, so it's not a problem. And here you have the part which corresponds to the adsorption to the on the molybdenum, and formally you have two bands which are in this area. So 2110 centimeter minus 1 and 2050 centimeter minus 1. One strong one and one smaller one. If you just perform the adsorption of CO on this type of surface, just on the very low, on the molybdenum with a very low coordination number, the interaction is very strong, and the frequencies that you can compute, it's below 190. So the system is not good at all to describe what is happening. And you have, before computing any properties, you have to be sure that the model that you are using is representative of the system in the experimental condition. And if we take into account the effect of the chemical potential of sulfur on hydrogen, we have shown that the number of at the molybdenum atom on the edge are not alone, and you always have one or two sulfur atoms that are adsorbed on this atom. And for the other type of edge that you can create, you have molybdenum atom here, and the coordination here is 4, and here the coordination is 6. And the none of the surface is equivalent to what you can just build by cutting your crystal. You always have a lot of reconstruction, a lot of adsorption, and that will depend on the experimental conditions. So it's important to take that into account if you want to build a model. And we have computed the frequency and the adsorption, and you see that uh, the difference are not so large from what is observed experimentally, and so it allows us to propose an assignment of the frequencies of the bands that have been observed experimentally. Wow. So it works quite well, but everything depends on the type of models that you define at the beginning. Another example, which is quite important, it's the alumina, which is a classical support for the catalyst. And one way to characterize this gamma alumina is to consider the OH frequency stretching mode on the surface of the system. And the spectra really depends a lot on the temperature. And I told you before that when we perform the calculation, we did not introduce any temperature in the calculation. So we have to use some trick to add the effect of the temperature. So if we start from alumina, we have here the example of a 111 surfaces of the gamma alumina, and you can absorb quite a lot of OH group on top of it. And the first second surfaces is quite the same, and the number of OH that you will absorb on the surface will depend on the temperature. And if you want to take into account the effect of the temperature, you will have to introduce this effect for the on the chemical potential on the molecule on the in the gas phase. And so you will not introduce, so this can be done using statistical uh, thermodynamics. We consider in general that the effect of the temperature on the solid is quite small, and that the most important effect is due to the evolution of the entropy in the gas phase. And you can see here that depending on the temperature, it can be seen here, when the temperature increase, the number of molecules adsorbed on the surface decrease a lot, and you go from something which is totally saturated to something which is completely bare without any water, going from 400 K to 600 K. So the evolution is quite rapid. And taking into account the effect of the environment, it's now possible to know how many molecules you have, and when you know how many molecules you have, you can compute all the frequency, and when you have all this frequency, you can propose an assignment on the system, which is not exactly equivalent to the assignments that have been proposed just based on the experimental data. But some of them are quite equivalent, some of them are not. And thanks to the calculation, you also know exactly on which type of surfaces the molecule is adsorbed, and since the two surfaces are not equivalent, their property may not be fully equivalent, and so it also gives you a way by considering the intensity of the different type of vibration to know to have an idea of the shape of the particles that you have created when you synthesize your particle. So it's quite good and it's worked almost correctly. We can go now to something which is more related to the project, and it will be high temperature electrochemistry. So since it will be high temperature, we shouldn't have so many molecules adsorb on the surface. So we will not have to take care about that. It's a good point. But the problem is that it will be electrochemistry. And we really need a way to introduce the potential in the calculation. Different methods have been proposed. Sorry. In general, the easiest way is what is called the grand canonical potential. It means that we will change the number of electrons in the calculation. By changing the number of electrons, we will remove some electron either from the Fermi level or add some electron above the Fermi level. And the evolution of the Fermi level will give us an idea of the evolution of the potential on the system. And so just by adding and removing electron without changing anything else, we will see the evolution on the evolution on the energy, and it will give us some way to check or to see the effect of the potential on the calculation. And another way to be sure that something is your system is correct is that here you should have a parabola, and so when you compute the effect of increasing on adding or removing electron, you will get a parabola that will also give you the capacity of your system, which can also be obtained experimentally. So it's a way to compare the theoretical calculation with the experimental data. So we just started to do that now. Another point for the project is we need to build a model, and we will start on the lanthanum, strontium, cobalt, iron perovskite. Uh, this is an example of materials that is used experimentally. It's difficult to get exactly this type of system theoretically because you will need a lot of atoms in your cell, and the calculation will be quite large. Uh, for in the literature, for the moment, one model have been proposed. So you start from a classical perovskite with in which you have La4, iron 4 or 3 or 12, and you just remove exchange one lanthanum by one strontium and one cobalt by one iron by one cobalt. And so it will be lanthanum 0.74, strontium 0.25, and so on. Sure. And you can build this type of system, but and you can define surface on which the reaction can occur. Here you have the reaction of one water molecule. Here you have the possible effect of transition metal or platinum cluster on top of this system. And here you have the type of surface that you can create. You can see that, however, the system is really well ordered, and you create layers or line with lanthanum and line with strontium, and you also create a plane with cobalt and plane with cobalt and plane without cobalt, and you also have a line of cobalt in your system. So the system is quite good, but you don't have a lot of flexibility to really see what is happening and how to consider the activation of O2. So using the same system, people have proposed some reaction mechanism that can be seen here. And once you have a reaction mechanism, you can compute the activation energy. So it's longer than just doing calculation on to get the nature or the vibration of the characterization of the intermediate, because you have to compute quite a lot of image to completely uh, compute the reaction path starting from the reactant to the product. But doing that, you will have an idea of the transition state, and once you have the transition state, you can characterize it by computing frequencies, and you can estimate the activation energy. And this can be done on the surface, or this can be done inside the solid. Here it's for the activation of O2, and here it's for the diffusion of the oxygen inside the system. Some important point also to add for this type of calculation. Uh, it's possible using the reaction mechanism to compute the overpotential, and the overpotential will depend on all the steps that you have used or proposed in your reaction mechanism. And the overpotential will depend on the difference between the lowest part, the lowest intermediate, and the highest intermediate. And this thermodynamic limitation will tell you if the overpotential for the reaction is high or low. And it's a way to also check if your solid is a good one or a bad one to activate either H2O or O2. Another point that will is very important is that this type of calculation can be also done by with a variation of the number of electrons. And so it will be possible to compute the effect of the potential, the external potential on the activation energy. And this effect of the potential in the activation energy is what is classically seen in the Butler-Volmer equation. It's the exponent that is used in this equation. And this parameter that can be computed at the atomic level can be transferred to a larger scale to the classical Butler-Volmer equation to allow the transposition of the result at the atomic scale to mesoscale. And I think that's all that I want to say now. Just to show you the system on which we are working now. So we started from the same lanthanum iron bulk crystal, but we define larger cell which allow to have more disorder for the position of the cobalt on iron, and also more disorder for the position of strontium on lanthanum. Doing that, we will increase the number of reaction sites and reaction environments and see how things are working. So we have started to do some tests on these classical surfaces, and we also want to see what happens for surfaces with higher energy, which may or may not, we have to check, be responsible of the activity of the system. And we will also this type of model will also be used to study the diffusion of the oxygen inside the bulk. And here we have quite a lot of possible environment, which is important to define the easiest pathway for the oxygen diffusion. So, arriving at the end. So I hope that I've shown you that DFT can be useful, but you have to take care about the parameter you use. You have to take care about the model, and you have to take care about the experimental conditions that you introduce in the model. It means that in order to get interesting and reliable results, we need a lot of discussion between theory and experiment to build something that is quite reliable. And I thank you for your attention.
Thank you. Great. Thank you very much, Jean-François, for this very interesting talk. We have some time for questions or
I may be a little too long. I don't check. Yeah.
yeah, but it was a kind of comprehensive presentation. Um, so if you have a precise questions or I don't know, it's always also
May
possible
I?
to. Yes, of
Yeah,
course.
yeah.
I was just curious to know if you have some idea of the amount of the XPS shift, just to have an idea how this can be compared to the experimental one.
It have been done on metals, and for the surface shift, the difference between the surface and the bulk can be around 0.5 eV.
Okay, so clearly visible
It's yes, it's
from.
visible. So if you have a
Okay.
synchrotron and you change the energy of your X-ray sources, you can see some evolution of your spectra, and it's possible to see that.
Oh,
And
that's
but for the system we are dealing with, it's important because we have quite a lot of transition metal, and I think that creating vacancy and things like that will have an effect on the oxidation state of the cobalt and iron, mostly cobalt, I think. And it may be a way to try to have to check if the model that we are using is correct or not by comparing it with the experimental XPS spectra.
Yeah, thanks. That's a very interesting way to correlate theory and experiment. Just another question, if I can. Do you think that is it's possible to have some idea of the trend of oxygen, of ionic conductivity from the mobility of the oxygen vacancies?
Normally, they are directly related. So if we compute the activation energy for the displacement of the oxygen inside the solid, it should be directly related to the conductivity and and also to the effect of the temperature on the conductivity.
Okay, thanks. Thanks a lot. Uh, just the final curiosity. Did you see any attempt to correlate the Butler-Volmer experimental and theoretical results?
Yeah, it's have been done. I didn't. I have seen some presentation about that, but I didn't find the paper. But yeah, and it's works quite well. You can have an idea of the effect of the. You can compute Tafel slope, and the results are in general quite correct. For the overpotential, it's not so clear. So the
Okay,
minimum overpotential that you have to apply to start your reaction, like it depend a lot on the reaction mechanism you propose, on the nature of the surface that you have considered, and the accuracy seems to be less. The
okay,
calculation seems to be less precise.
okay. Thanks. Thank you very much, Jean-François.
Paolo?
Uh, yes, indeed. I had a question, but the discussion with Antonella gave me another opportunity for a different question that frequently comes to my mind because I understand that your simulation are basically thermodynamic simulation, let's say equilibrium states,
Yeah,
while the ionic conductivity involves time. That is
yeah,
not just how vacancy can move, but how fast they can move. And
yeah.
that can be accounted for by the simulation.
Yes, because it the rate of the displacement will depend on the number of vacancy and will also depend on the activation energy for the displacement for the hopping from one side to another one. And we can compute that. And after that, it will be quite equivalent for the to consider to get the reaction rate. We just have to use statistical thermodynamics. And it will be equivalent to what is done just when you consider, for example, the adsorption of a molecule on the surface. And normally, it's not so bad. What is not directly included, I haven't checked, I haven't seen that, is how to introduce the effect of the potential on the conductivity. Because you may also have an effect, but I don't think it will be so easy to compute the effect on the potential on the mobility. Because the way we are doing that, we just change the number of electrons, but we don't introduce field. And so for displacement of ion, the electrostatic field is also important. So that may be that will be a limitation, I think. Uh,
Yeah.
it may be possible, but for the moment, it's not so clear.
Actually, the question that I wanted to ask you was concerning your conclusion. You say that DFT can be useful, but and there is a list of obstacles. And there are
Yeah.
three items. Say if I know this, if I know that. Which one is the largest obstacle in your view, particularly for
The
our application?
the the most important thing is to define correctly the model. Because if you don't choose correctly your parameter, yes, you will have some deviation, but the result will still be correct in any case, normally, except if you are doing completely wrong. But normally you don't have so many problems, and by default the program don't want to do calculation completely out of the scope, so it's okay. But if your model that you use is not well defined, you will get interesting results, but not for the model you wanted to study. Typically, if you consider the system with perovskite and you don't put any cobalt on the surface, you are going back to a classical iron lanthanum perovskite, which is not the model of which is not the system we are interested in. So the most important thing is the way you define the model, and that's why we really need quite a lot of input from the experimental part to be sure that the model that we use is correct. After that, we know how to do the calculation and how to get some relatively reasonable results. But if the model is wrong, the results are good, but not on your system. And for example, it's a system, it's some calculations that have been done when you are doing calculations systematically. If you start from MOS2 and you can exchange the molybdenum back whatever you want in the calculation. And people have discovered that when they exchange the molybdenum by something which is an atom that can be at the +4 state, seems calculation, you don't change the coordination of your system. If you put atoms that don't want to be +4, it becomes easy to remove sulfur. But the problem is that you will never manage to build your system at the beginning, because you will never have, for example, calcium +4 in your system. For the calculation, it's not a problem. It means that the calcium takes the electron and the sulfur are losing them. But if you want to build it, it's not possible. So what is important is really the chemistry and how you build your model.
I think that time is running, so I suggest that if you have other questions, do not hesitate to get in contact with Jean-François or just pay a visit. Everything can be organized. That is possible, or you can invite Jean-François to give a talk at your facility. I'm sure it will be.
And Lille is not so bad.
Yes, we can arrange all of these kind of things. Okay, thank you very much, Jean-François. And I would like now to introduce Paolo Canu. He is a full professor at University of Padova and mostly interested in modeling kinetics and also middle scale modeling. So please, Paolo, you can share your screen and we are all listening.
Can you see the screen?
Yes.
Everything is perfect, Paolo.
You see the whole slide, or you also see a small window with your face?
No, just a big one.
Okay. Because I also see a small inset into the screen where I see Elise.
Oh, I can
no
switch
problem.
off my camera. That would be.
No. It's not the issue. It's apparently the way of sharing. But the annoying part is that is masking part of the slide that I see. But anyway, thank you for giving me the opportunity to tell you about what we are doing here in Padua within the KNOWSKITE project. And I would like to start reminding you of a few keywords that are typical of this project, just to put the contribution into the right framework. And the KNOWSKITE is mainly addressing general methods, but applied to solid-oxide fuel cell and electrolyte cells, mostly based on perovskites. So that's a type of application and material we will talk about. There's some emphasis of trying to understand the interconnection between reactions and transport of charges, ions, and species within regions that might involve porosity, that are typically of the electrodes and electrolytes. And there's an attempt to combine modeling and experimental technique of characterization of the material. So trying to match the two, as Jean-Francois mentioned at the end, we always need to interact between modeling and experiments to understand each other. We are also trying to implement some advanced technology like machine learning and artificial intelligence tools to take more from the data, the results that we are collecting, both at the experimental scale and on the modeling scale. And there's definitely an attempt to move to an industrial scale. So not pure science, but hopefully applied science. So the type of object we are trying to describe, ideally it's a stack that could be a fuel cell or electrolyzers, which is basically an arrangement of many different cells that may have different shape. But what will be constant in our presentation is that they will be made of solid oxides. At a smaller scale, typically the laboratory scale where the people in the group are collecting data, we have simple arrangement of the so-called button cells that conceptually are an arrangement of two electrodes and electrolytes, each one facing a different stream of different gas. The concept can be realized by different devices. That's one example that one of the partners of the project is developed in the past and I guess is commercializing. And it's quite close to different devices that I guess someone in the project has and for testing the materials. The goal of the modeling at different scales, as outlined by Jean-Francois, is to connect experiments with some theory. And the first step is trying to formulate a mechanism of what's happening into your experiments. And that's just the beginning of modeling, trying to develop a concept, a representation with some assumption, of course, of what the processes, the physical and chemical processes taking place in your experiments. Then turning this mechanism into some equation. And the equation requires suitable tools to be solved. They produce some numerical output that must be comparable to some extent to the experimental measurements, and finally suggest by a match with the experimental results some improvement in how we understand and we explain what's happening. So within a virtual or circular path of gradually improving our understanding, but at the same time also the design of new materials to improve performances. I'll tell you what we are doing on the intermediate scale of modeling, taking as an example a reference cell that is based on hydrogen as a fuel. That's a fuel cell. Hydrogen as a fuel, possibly with some moisture, and air on the other side, on the cathode side. The cathode can be made of the last material that has been mentioned also by Jean-Francois, that is lanthanum, strontium, cobalt, ferrite, and both the cathode and the anode are composites, so they are a mixture, a solid mixture of different material. One mainly intended to be an ionic conductor and the other mainly an electronic conductor. In all cases, including the electrolyte, we are always talking about solid oxide. That's a type of application at intermediate temperature, but still they are fairly high, so it means that all the reactant and products are gases. And in addition, the application that I will tell you about is based on the transfer of oxygen ions and not protons. Actually, the difference in the modeling is not significant. The paradigm are the same, but in this case, where we are giving a name to the materials in the cathode, the electrolyte, and anode, in this context, the fuel cell is transferring oxygen ion, sorry. Starting from this idea of what could be the operation of the fuel cell, we need to first draw a sort of mathematical description. And the first step is to build a geometric description of this. So you see this shadow area, it's like a plane cutting the cell that can be described like in the right part of the slide. So that's the plane representation set on a symmetry axis and describe the free gas channel on the cathode side, the free gas channel on the bottom side. These gray area are simply a section of the pipe that isolate the inlet from the outlet on the anode side and the inlet from the outlet on the anode side. Then the cell involves two electrodes on the cathode and the anode and the electrolyte. The thickness can be changed, so it can be an anode supported, an electrolyte supported, a cathode supported cell. That's the first step in building a mathematical description of what's going on there. There are many different processes taking place within this cell. There's a gas flow entering and leaving on both sides, on the cathode and the anode side. So pure gases flowing into this region. There's a gas flow also within the electrodes that are porous, so there are empty spaces in between the solid particles that have been compressed together, allowing some oxygen on the cathode side and some hydrogen and steam on the anode side to permeate through the porous matrix. And definitely there's no gas flow in the electrolyte. Actually, that's one of the weaknesses of these devices, that they should be gas tight for the two sections, and frequently that's not so easy to be accomplished. Within the electrodes, there are surface interaction and reaction. That means absorption, surface diffusion, and charge exchange reactions that might also involve the bulk of the materials within the electrodes. We also need to take into account the transport of charges, free charges, electrons, in the electrodes and in the current connectors. There could be some displacement, transport of ionic species, both within the electrode and within the electrolyte. And finally, there could be also some heat production or consumption because of the reaction taking place within the electrodes. All these processes affect one each other, and they are all coupled. So we need to develop a way of accounting quantitatively for all these steps simultaneously. That means developing what is called a multi-physics modeling, where multi-physics means all these processes together. That could be general enough to allow modification of any property within our model. Starting with the simplest part, the gas flow in the open channel means that the air will enter. Some oxygen will enter into the electrode, might react, and the residual oxygen will leave from this side. The same description occur on the anode side, where a stream of gases enter and leave and continuously, let's say, wet the surface of the electrode, provide the fuel at the bottom and the oxygen on the cathode side so that the electrode can work. The flow outside of the electrode is quantitatively described by a few equations. The first one is the conservation of mass, which means that the mass, the total mass entering from this side and leaving from the other side must be combined with the velocity, so that if we are losing some mass, then the velocity will change. But what is important is that there's no reaction in the yellow area, where the yellow area do not include the electron, not just the empty channel. Additionally, there's a balance of forces called momentum balance, and the set of this equation altogether is called Navier-Stokes equation, that will tell you the local distribution of velocity. And this includes basically the main driving force for displacement, which is the pressure gradient. So air can flow through this region only if you are pushing from this area. That means there's a pressure higher than on the other side. At the same time, there are some dissipation with the contact with the walls that are normally viscous resistances, so they are dominated by the viscosity. There could also be some volumetric forces, typically gravity, that is normally non-relevant in a pressure flow, and particularly for gases that have a low density. So this set of equations allow it that in practice for a axisymmetric configuration is a set of three partial differential equations allow to predict the velocity at each point in the channel, but also the amount of oxygen flowing through the electrodes. And although not particularly relevant, the pressure drop, so the amount of pressure required to force the gases to flow through the channel. But there are not usually significant resistances to flow in this compartment. There's also a process of gases moving within the electrode because they are porous. That means that the electrodes must be permeable to gases, so they must allow some empty space for the gases to permeate through the texture of the electrode, that are essentially made by compressed powders. So they indeed allow for some room, even very narrow, let's say pores, for the gases to flow. It's extremely relevant to describe the flow within the electrode, the texture, that is how powders have been packed together. So the amount of empty space and the tortuosity of these pores. So in a magnified picture, we are now discussing about on the cathode side of the oxygen that is trying to permeate through the empty spaces between the composite made by the ionic conductor and the electronic conductor. Because it's not possible to describe each single particle, The common assumption at this scale is to describe the electrode as a pseudo-continuous area, so you are not identifying individually each single particle of one material or the other, but you are assuming that there are some mean properties summarizing the ease of permeation through this material. So there are parameters called permeability or porosity that describe on the average the behavior of the electrode. There's a lot of research about being able to predict the real structure of the electrode, starting from some ideal model of spherical particle randomly packed and compressed. So these parameter, porosity and permeability, might be predicted from some theory, but definitely it's much better to try to measure them. In terms of equation, the mass conservation of the total gases within the electrodes contains an additional term. So basically it says that the flow of gases overall might change because some gases disappear, and they disappear because there is a net transfer of mass from the gas phase within the electrode to the other compartment, because the ionic conduction brings mass from one side to the other of the cell. In addition, there is always the momentum balance within the electrodes that is allowing for the creation or consumption of total mass because of the transfer of mass to the other side. And the most relevant part is this permeability parameter. So we already see that the parameter mentioned, porosity and permeability, appear into the equation, and they basically determine how easy would be the transport of species across the porous electrodes. Once solved this additional equation within the domain of the electrode, they are allowed to predict the internal velocity, although it's not so relevant because if the electrolyte is gas tight, so there's no possibility of total gas to flow beyond the electrode, the velocity inside the porosity is fairly small. So the whole set of this equation is not so important. It is more important to look beyond the total gas flow to the single gas species that may travel and react. Single gas species are in the gas compartment. They are within the porosity of the electrodes, and there should not be any gas within the electrolyte if it's operating as expected. So the description of how single species move in the gas compartment is given at steady state by this equation that basically says that the single species might diffuse or might move together with a whole stream, and they cannot be consumed or produced within these domains. There's no reaction. The reaction is within the electrodes. And indeed, inside the porous electrodes, we have an additional term in the equation that describes the rate of production or consumption of gas species. Now we are talking about the species appearing on the sketch: oxygen, hydrogen, steam. Not on intermediate on the surface. these are single gas species. So focusing on the electrode, the equation says that the species might travel, that's the transport of species, and the displacement is based on diffusion. The driving force for diffusion could be a gradient of pressure or a gradient on composition. But what has been shadowed now are the contributions that are negligible within the electrodes. So the convection, the transport of species because of the overall movement of gases within the pores is negligible because the velocity inside the pore is indeed small. So diffusion is ruled by the gradient of concentration. Oxygen will penetrate into the electrodes just because you expect a higher concentration close to the electrode surface compared to the concentration down within the electrode. The diffusion is described by an effective diffusion coefficient, which is connected with the actual molecular diffusion of oxygen into a mixture of oxygen and nitrogen. But within the electrode, described as a continuous area, we have an effective diffusion that is corrected through some information about the texture of the electrode. A more sophisticated model is the so-called dusty gas model, where the diffusion into the electrode is a combined Knudsen diffusion for very small pores comparable to the average size of the molecules, and the ordinary diffusion, but corrected through the porosity and the tortuosity. So the parameters that have been called, actually put into squares, are critical parameters that determine the output of the model, and they should be somehow obtained from experiments. On the reaction contribution of single species within the electrode, we should account for any path where oxygen on the cathode side or hydrogen and steam on the anode side can be consumed or produced. Now there are two approaches. One is a sort of simpler one, where within the electrode we expect a consumption of oxygen on the cathode side, hydrogen on the anode side, through a sort of reaction taking place uniformly within the electrode. That is essentially based on a global electrochemical reaction, and the rate is measured by some simple expression like Butler-Volman 1. As an alternative, which is the frontier we're working on the line of many other that did this type of approach before us, trying to describe with much more detail what's happening on the surface. And that will be the interface with Jean-Francois, where elementary step on the surface might be described with some fundamental model of representing the real atomic structure of the species. From the point of view of gas species, that is oxygen and hydrogen, the only possibility of having a consumption through a detailed microkinetic model is because they adsorb on the surface. And from that point onward, there will be much more detail of chemistry and electrochemistry on the surface. But from the point of view of the gas phase in the voids within the electrodes, these species disappear just because they stick on the surface and start detailed mechanism of transformation. So just to give you an idea what is the first approach based on a single volumetric reaction, the rate of production or consumption is based on a single rate of reaction that for an charge transfer reaction can be described in terms of current, so number of electrons, and of course you will convert into moles by means of the Faraday constant and the stoichiometry. So for example, in the anode side, the hydrogen by means of this global reaction is assumed to react with oxygen ions coming from the cathode side, and the rate of production of hydrogen, it's indeed negative, so it will be a rate of consumption that is proportional to the length of the triple phase boundary and the intensity of the current at the triple phase boundary corrected by the Faraday constant. And the rate of production of hydrogen is the opposite of the rate of production of steam. And because the first one is negative, this negative of the negative becomes a positive, so steam is produced at the anode. Typically this current density at the triple phase boundary is described by a Butler-Volm expression that is semi-empirical, but is essentially based on the assumption that the whole electrochemical process can be described by a single reaction. And by the way, it's also hides somehow the idea that the rate determining step is the charge transfer reaction. On the other hand, the approach to the consumption of species, gas species within the electrodes, means that the rate of production is the opposite of the rate of absorption. So on the cathode side, that means that oxygen as a molecule in the gas phase can interact with the surface side. In this case, I took an equation mentioning LSM instead of LSCF, but the concept is the same. That's a surface side on the typically on the electrical conductor part of the composite, resulting in the absorbed oxygen on the surface. And that's a process of removing oxygen from the gas phase, bringing it to the surface. But I'll give you some more detail later about this implementation. Let's see another process that we need to take into account, that is the transfer and involvement in a reaction of charges, electrical charges, that will take place within the electric part of the composite in the electrode. So in our case, it's LSCF. In many other cases studied in the literature, it could be LSM. And also, but it is quite marginal because the transfer is too fast in the current collector that are normally placed above the electrodes. While the ions, they can move within the electrodes and within the electrolytes. I mentioned that you might have proton exchange or oxygen ion exchange cells. Now we are focusing on an oxygen exchange, but the concept is the same. We need to take into account the fact that these ions are moving from one side to the other. And a sketch already presented before is that the electrons are moving along the electric conductor through the contact between each single electric conductor particles, while the ions move through the ionic conductor that include also the electrolyte. Quantitatively, in terms of equation, the transport of charged species involve at steady state a balance that says that the current, the stream, the flux of ionic species is equal to the production or consumption. And the flux is ruled by the ionic conductivity multiplied by the gradient of potential. And this ionic conductivity must be determined across the anodic, electrode, the anode, the cathode, and the electrolyte. And all these properties are quite difficult to be measured, and they extremely determine the output of the simulation. And they can also be locally changing as a function of temperature and the local potential. On the side of transfer of electrons, the equation is similar. The balance of inflowing and outflowing stream of electron in a small elementary volume is equal to the rate of production or consumption. And the flux, it's also proportional to the local gradient of potential, and an electrical conductivity that must be, again, determined for both material of the electrodes. That is exemplified by this sketch where we see the electrons traveling along the electrical conductor part of the composite, and the dashed line is the path of the ionic conduction, which occurs through the material that has ionic conduction. And within the pores, there's diffusion of species in the gas, up to the triple point where the reaction takes place. Of course, also the electrolyte is able to allow for some transport of charged species, but just ionic species. The gradient is the local potential that is affected by the flux of species, both electrons and ions. So the solution is not so trivial. Now, going back to more details about the reaction of ions and electrons, I mentioned a global approach based on a single global reaction, like this one, that is described by current density that basically assumes that the charge transfer in the whole process is the rate limiting step. And this current will determine the production or consumption of both ions and electrons. So they are responsible for the Faraday current density. But let me tell you what it means describing the overall production or consumption of species L or S, so electrons or ions, locally, by means of detailed elementary kinetics. That means that the overall current locally is determined by many different steps, requiring a detailed description of what's going on. These are some examples. That's one example of a mechanism, a detailed mechanism on the cathode side, where the oxygen as a gas is assumed to adsorb molecularly on the the electronic conductor, then split into oxygen adsorb, diffuse on the surface up to the three-phase boundaries, and then combine with surface sites and later vacancies on the ionic conductor to finally determine the flux of ions within the ionic conductor. So that could be a description of each single step where you see the molecular absorption, then the splitting of the oxygen, the molecular oxygen adsorbed into atomic oxygen adsorbed, the surface diffusion, the reaction at the triple phase boundaries with a surface site on the ionic conductor to produce the oxygen ions within the ionic conductor, and so on. So that's a more detailed description of what's taking place within a single species into the electrode. Another example on the anode side could be this one, where you see the list of reaction on the surface of the ionic conductor, on the surface of the electronic conductor, and the list of all the charge transfer reaction that might take place. Of course, for the same system, you might suggest different combination according to different hypotheses that could be suggested by some studies like the one that Jean-François is doing. Finally, each single step will be described by a rate that is proportional to a forward rate constant and the amount of reactant minus a reverse rate constant multiplied by the amount of products, and the kinetic constant must combine an Arrhenius contribution and an electrochemical part where the difference of potential between participating phases it's involved, and that's the type of information that must be matched with the Jean-François simulation. So that's one example again from the literature where some value of this parameter have been suggested perhaps from previous work, or they have been simply adjusted so that the model is trying to get as close as possible to experimental data. So in summary, the model is expected to produce information about the velocity of the gas in the channel, the composition of the gas in the channel and within the porous domain inside the electrodes, the distribution of potential, and more closely to the actual experience of the laboratory, the model should produce some macroscopic information like polarization plots or Nyquist plot that are direct output of experimental technique normally used in the experimental practice. So the model is made by a number of partial differential equations that are coupled that must be solved in the simplest description of the domain that should be at least one-dimensional. In the case that we develop is two-dimensional, including a radius and an axis. Another important feature is a steady-state simulation or a dynamic simulation, where the steady state is useful to predict polarization curve, while the dynamic, more sophisticated implementation of the model allows you also to describe transient that are typical of an experiment like impedance spectroscopy, where there is a perturbation of the applied voltage just to sample how the experimental cell is changing the impedance at different frequencies. The model allows also some parametric sensitivity study. That means you can see what will be the effect of having a higher or a lower porosity in the cathode or in the anode, having a higher permeability, having a higher temperature, and so on. That's mainly the main usefulness of the model, making predictions that of course will project the assumption included in the model. So they are not expected to be completely true, but they might suggest improvement in the explanation of the processes described in the model. And by means of these studies, on each single step, and also the comparison with experimental data of impedance spectroscopy, we expect to identify the single sub-processes that might be controlling, whether they are gas diffusion or surface diffusion or charge transfer or anything else. And that is important to design new material to improve performances. Just to give you a brief overview of the type of results, that's a typical output of the gas velocity in the channel. Not particularly useful. That's exactly what we were expecting. The flow will be regularly from the inlet to the outlet with some stagnant region close to the electrode. And that's not immaterial, because a low velocity here means a poor supply of oxygen to the electrode. That is similar also to the other side. So probably this configuration that is called stagnation point, because you're feeding a gas against a wall, so the gas must diverge and flow from the periphery. It's leading to a stagnation region on both sides that is not useful to make sure that the oxygen or the hydrogen in front of the electrode is sufficiently uniform. The model can predict also the distribution of ionic potential, and that's already a sensitivity analysis on the over voltage. And you see that that's a magnification on the electrode and the electrocathode and anode on both sides. And you see the distribution simply by color that tells you the difference in potential. At increasing over potential, their gradients are larger and larger. And of course, if the gradient of ionic potential in the cell is increasing, you would expect a much higher stream of ions through the cell. The species, gas species, oxygen and hydrogen within the electrodes are barely appreciable on this scale. So you need a magnification to see the electrode, and at low polarization, you see that the concentration, which is described by the color, of oxygen in the cathode and hydrogen in the anode, it's almost uniform. So there are not significant gradient. But if you increase polarization to a very high polarization, then you will see that the oxygen starts decreasing from the free channel, approaching the surface. And if you enlarge the surface, you see that it's also going down to almost zero within the electrode. So that's a case where the cathode is starving for oxygen. There's not oxygen enough if you are forcing the cell to operate at a higher overpolarization. That is reflected also to some concentration polarization on the anode side, where you see the gradient of hydrogen that is not so dramatic as in the cathode side. The reason why this configuration is of concern is because you are basically wasting the electrode. Most of the electrode is not working because there's no fuel, there's no oxygen or hydrogen enough for the electrochemistry to proceed. The model is also able to predict polarization curve starting from the open circuit voltage. We can identify all the over voltages due to concentration, activation, and ohmic. And the prediction is the blue line, and that is immediately comparable to experimental measurements. We can also predict a property that is impossible to measure. That's the concentration of hydrogen within the Oh no, sorry, that's the concentration of hydrogen in the output of the anode compartment, and that's the concentration of oxygen in the output of the cathode compartment. And we see that increasing the overall voltage, the consumption of hydrogen and of oxygen increases, and the consumption is non-linear. That's the effect of increasing the amount of air fed on the cathode side. And we see that the consumption of oxygen is increasing. And as a side effect, also the consumption of hydrogen is increasing, mainly because of a higher flow rate of oxygen in the cathode compartment increases the convection. That means more oxygen reaches the electrode, supporting a higher activity of the electrode. That means a higher current, so a higher consumption of both oxygen on the cathode and hydrogen on the anode. Let me skip a few. That could be interesting, which is the impact of the porosity in the cathode. And we see that in terms of polarization curve, the porosity makes a difference. And that could also be seen as an opportunity to compare with experimental polarization curve and see the impact of having a higher or a lower porosity in the synthesis. Again, the porosity is expected to impact the diffusion, which means how easy the oxygen can penetrate the cathode and then support the electrochemistry, improving performance and then the current. The same type of information can be seen in terms of spectra of impedance, where according to the model, change the porosity shift the spectra and also modify somehow the shape. So that's an opportunity to have a first principle description of what is the output of the experiment, that is the impedance spectroscopy. So providing a mechanistic explanation of the experimental measurements. Okay, I would like to, that's a test on the thickness of the cathode that shows essentially that the cathode has a dramatically is controlling. So indeed, this few example tells you that for the set of parameters used for this simulation and some sensitivity analysis, we were able to confirm that this configuration is limited by the cathode. So the efficiency of the cathode is controlling the overall performance of the cell. And indeed, having the possibility to modulate the porosity of the cathode and also changing the length of the triple phase boundary would be beneficial to improve the performance, while any improvement on the anode side is not so effective. Overall, I would like to conclude saying that the model, this type of modeling, is interesting because of the versatility. Now I told you some simulation done on this specific configuration based on CGO and the nickel and on the anode side and LSCF on the cathode side. But in principle, we can easily switch to other configuration as far as we know the property of the materials involved, including the possibility of accounting for proton exchange cells. The model, through the comparison with experimental data, can allow to identify which are the physical or electrochemical process that might be controlling. When I say physical, I mean the conductivity of charges, conductivity of ions, so processes that are not involved with the transformation of the species, but just the displacement across the gas or across the solid oxides. So overall, the main purpose of this modeling is to support some theory-based, some rational design of the synthesis of new materials. But on the other hand, there are some details that are not so easy to be controlled. Particularly, the model, to be meaningful, need to closely match the experimental data, so need to be validated constantly against experimental data. And that means that we need some property of the parameters involved that need some specific measurements. And finally, there's a lot of space for improvement if the electrochemistry is described with more detail involving a breakdown of the whole process, the overall process, into single steps, and hopefully having an estimation of the value of the parameters involved in each single step supported by theory. That is from Jean-François. So these are the people that did this contribution. I would say that I was the speaker, but the guy that did the work is Andrea. So probably you should thank him and not me, but I will thank you for your attention.
Thank you very much, Paolo, for this really exciting talk. I guess there are many questions in the audience. Can you raise the hand or just talk? So Bernhard was raising the hand.
Yeah, thank you very much for the very interesting talks to both of you. I have one question to Paolo for your recent talk. This model that you created with Andrea, what is the runtime for one simulation, and what is, in your opinion, the most computationally expensive part?
Well, of course, the proper answer to this question must be given by Andrea, but I can tell you there are two types of simulation. One is a steady state simulation with some computing time, and another one is the transient one. Although there are some facilities for this type of transient that are basically oscillating simulations that allows also the transient simulation to be fast enough. Overall, just to give you a single number, I should probably tell you that it's in the order of tens of minutes. Am I right, Andrea?
Yes, you're right.
On an ordinary computer, desktop computer. Because we take advantage of symmetry, that's the trick. You should reduce the size of the computation, just describing the simplest subdomain that is representative of the cell. And it's still a two-dimensional simulation, while many results suggest that it's mostly one-dimensional. So it could also be reduced to a single line without losing so much accuracy.
Thank you very much.
Antonella, you wanted to ask a question as well?
Yes, I have a couple of curiosity. I appreciated your presentation and I like it very much. I was thinking which can be the effect of substituting of having a mixed ionic conductor that should increase the triple phase boundary region. And also if we change the charge carrier and we go, as an example, thinking to the proton ceramic, how much can be the effect on the modeling?
I'm expecting that simulating MIEC, so mixed ion and electric conductor, should be easier. One of the main weakness that I see in detailed chemistry is that it looks like everybody is suggesting steps that I don't know whoever will be able to check. Probably, I'm sure that you saw in the sketch that even in the ionic conductor, they were accounting for a transfer of vacancies. That I don't think is a relevant process, but in the detailed steps, you can believe that there is surface diffusion, bulk diffusion of charges, of ions, whatever you like. And of course, if you have a mixed ionic electronic conductor, I would say that I'm expecting a reduced set of possibility of assumption of different mechanism compared to the composite, where you have two species with all species, the electronic and the ionic, that could be assumed to transfer species on the surface in the bulk of vacancies and so on. So I see some degree of uncertainty and ambiguity in the mechanism. From theoretically, breaking down the whole process into single step is extremely powerful, but identifying which type of steps are relevant and which are something that you dreamed the last night while sleeping is quite difficult. And of course, if you have two types of materials, there are much more combinations that you can try, while a single material should reduce the set of assumptions about the mechanism. That's my general expectation. And from the point of view of protonic conduction, again, the model remains with the same type of equation. The question is, what is the real mechanism of transport of protons through the electrolyte and through the materials at the anode and the cathode? So the weakness is not in the formulation of the model, but it's in the formulation of the mechanism by which ions, oxygen ions or protons, vacancies, charges, and so on move within the materials. So it's like the model, it's a framework that can account for any type of transport process and chemistry. But the weakness is then suggesting what is a likely chemistry and what is a like electrochemistry for that type of material. And that's where some more fundamental approach like the one of Jean-Francois should be helpful, at least qualitatively, to suggest what is likely and what is not.
Thanks a lot.
Thank you very much. I think that Jean-François and then Siavash wanted also to have a question. So Jean-François.
Yeah, well, just maybe more comments than a question, but there are some trick in microkinetic modeling to check the importance of some of the reaction and to see on which reaction step you have to focus if you want to see some evolution on the total reaction. So I think it may be useful just to try to apply that to simple model just on the kinetic or microkinetics and just to extract one global reaction, which even if we don't have to detail everything, it may be useful.
Yes, sure. You still need to be in contact, both of you, for sure.
Yeah.
Definitely. Siavash, you also wanted to ask.
Sorry, there was a student at the door and knocking insistently, and I had to stop him. I think I understand what you mean, Jean-Francois. That's called the sensitivity analysis on the parameter of the kinetic model. So the model allows you to test what the effect of doubling or halving a pre-exponential factor or and activation energy, and see which steps in the detailed chemistry could be more or less relevant. So we know it can be done, and indeed the possibility of the model to run fairly rapidly, it's interesting, particularly for this type of analysis, sensitivity analysis.
Yeah, because it can also tell us from the chemical point of view on which part of the reaction we have to focus if we want to improve the system.
Yes.
Definitely, thank you. And then I think that Siavash has a question maybe for Paulo or Jean-François or both.
Yes, hello everyone, and many thanks for both presentation. I was thinking, is it relevant to consider the effect of heat generation from the reaction and its effect on, for example, ionic conductivity, or its effect again on the reaction rate? So it's like a two-side balance. Do you think it's negligible or it's important to consider?
Yeah, thank you for this question. Indeed, I mentioned at the beginning that we should also take into account the distribution of temperature, while in the end, I never mentioned the temperature because indeed we simulate assuming it's isothermal. Actually, I don't believe it's isothermal because actually it's a combustion. So there's an enthalpy of reaction that is significant. But we should, from the engineering point of view, make a calculation, even a simple calculation, of what is the amount of heat that can be released following that amount of consumption of hydrogen compared to the total flow of gases. So it might be that there is enough flow of gases to remove easily the heat to assume that isothermal operation is reasonable. But you're right, that's a lack of the computation so far that we did not check how reasonable is the isothermal assumption.
Okay. And the second question, have you ever, or let's say, is it possible to uh, consider the shape of porosities, not only the volume fraction of porosities?
That's what is tentatively done by the so-called tortuosity. You saw that I mentioned there is a tau called tortuosity, typically introduced to estimate the effective diffusivity into a porous domain. And the tortuosity is an empirical approach to describe the shape of the pore. So porosity is the amount of voids into the porous region, while the tortuosity tries to summarize how tortuous or complicated are the path of the pores. But it's quite empirical.
Okay. And last question, because a few years ago I was using COMSOL multiphysics for modeling of solid oxide fuel cells, and just out of curiosity, actually I cannot remember all the details at the moment, but I remember I would use Brinkman equation instead of Darcy, but you mentioned Darcy for the physics part of the job.
No, actually, the equation that I reported is the Brinkman one, but I suggested that the contribution of convection is not that relevant, so that eventually you're not even using the Darcy one. You are basically assuming that there is no flow, net flow of gases into the porous region. It's mostly diffusion.
Okay. Okay. Thank you very much.
Okay, thank you, Siavash, for the questions. Does someone want to add a comment or have a question? I'm just checking among all the participants. I think no. Okay, so once again, there will be a recording and it will be available within the consortium, maybe with the authorization of everyone. Some fragments may be made public, but this is to discuss with Laura and Claudio. Of course, do not hesitate to get in contact with each other for further discussion or further interaction. Of course, I know that Siavash, you will soon have your EIS implemented, so you will be able to provide a lot of experimental data to Paolo and vice versa. I'm sure that Paolo will be happy to build models out of your and try to get the first principle curves. That would be really fine. I think it's already a bit more than 2 hours that we are discussing. I don't know if there is anything to add, if someone wants to add anything, or I might conclude. Maybe. Yes, firstly, we intended to have a round table if it was kind of public thing, but we can, all of us, we can have side to side discussion. So I don't think it's worth going now for round table. I hope you agree with me, Bernard.
Yes, absolutely.
Okay, great. And speaking of Bernard, our next webinar will be on the help and what can artificial intelligence do for people working in materials optimization or materials design, especially for functionalized materials. If I'm right, we haven't a date specified now, but it should be somewhere in June. Am I right?
Yes,
Or
the
I'm
latest. The
Yeah,
latest.
okay. So I think that we will soon, this time it was our first experience
Mhm.
in doing a webinar and we were running out of time. However, I hope we can, within this week, find ideal date or the least bad dates for the webinar in June and start organizing and communicating around this next webinar. I would like to thank you all for participating and of
Thank
course,
you.
thank again our today's speakers, Paolo Canu and Jean-François Paul. And do not hesitate to get in contact with them. I remind you that we all have the contacts of everyone on the SharePoint, and it's updated every day, updated list. So do not hesitate to have a look and get in contact. There are also programs for inviting professor or visitors besides the project, so do not hesitate as well to play with this kind of possibilities.
Okay.
Okay, I would like to thank you all again, and I wish you a great afternoon. Thank you again, and yes, let's meet on firstly our exploitation webinar. It will be if I'm right, the 23rd of April.
23rd. Yeah.
Yes, exactly. So we'll meet again, and then in June for the webinar on artificial intelligence enabled materials research. Thank you
Okay.
very much.
Thank you all.
Thank you.
Bye.
Bye
Thank you
bye.
Bye.
very much.
Thank you.
Bye bye.
Goodbye.
Thank
Bye.
you.